We're continuing on here with chapter 9, which is solutions. So we got a little bit into solutions last time. So remember that a solution is really the guy that gets that sort of aqueous symbol next to it. And as we talked about last time, there is a difference between something that is aqueous and something that has the liquid designation next to it. Again, something that has the liquid designation is just a pure substance by itself. Something like water by itself has the liquid sort of designation. Again, if we take something like water, as we talked about last time, and some say solid sodium chloride, which is salt, and put them together, the salt will dissolve in the water, and that will result in a sodium chloride solution that would get the aqueous sort of symbol next to it. So aqueous usually implies a solution, which is a homogeneous mixture. That means it pretty much looks the same throughout. Everything sort of dissolves and everything looks like one sort of phase. There really is kind of two parts to a solution. One part is what is known as the solute, and that is the smaller part of the solution. So in this example here, it would be the sodium chloride that would be the solute. The other part of the solution is the solvent, and that is the larger part of the solution. And in our example here, water would be a solvent. As we talked about last time, water is a really good solvent for a lot of things that are ionic, for example, things that are polar. But again, it's not always the best sort of solvent. So what happens in a situation like our sodium chloride example, when the sodium chloride goes for a swim, again, it will break apart into its ions. And what ends up happening, as we talked about last time, is because water is a polar molecule, that means there's a positive side and a negative side to water. Basically, the negative side of water, which is the oxygen side, will surround the sodium ions in solution. The positive side of water, which is the hydrogen side, actually will surround the negatively charged ions in solution. And really, this does a couple of things. This really is when we sort of put something like salt into water and it sort of disappears or dissolves. That's what's really happening here, is a ton of water molecules is really just surrounding all the ions. And it no longer is sort of visually apparent to us that there is salt in that actual solution. It also prevents the really strong attractive force between the sodium ion and the chloride ion, the electrostatic attraction between those two ions, which is extremely strong. It also keeps those ions apart from one another, kind of acting almost as a buffer between them to prevent them from coming back together. And that's really when we take something and dissolve it in water, sort of what the situation is occurring. As we talked about, we sort of speed up this process up a little bit as we go to dissolve something, right? Again, we typically will perhaps stir it, and stirring it obviously throws a lot of water molecules all over the salt, allowing this interaction basically to occur. It also supplies a lot of energy as well when you do that. So it allows, again, this dissolving process to occur really well. As we talked about, making of a solution really is sort of a physical process here, right? Because we could, in this example, evaporate off the water, and those ions would come back together, and you would get your salt basically to return. And that would be what would happen if you took some sodium chloride solution and you put a Bunsen burner, also known as a triangle, at the end of a line here. And we start heating this again, basically we would just start evaporating off all these waters. And at that point, there's really nothing to stop this really strong attractive force from the sodium and chloride ion coming back together. And what you would have ended up seeing is probably not red, but more of a white solid that would come back, in your beaker and stuff like that, because you basically evaporate off the water. The water was lost as steam. It didn't really go anywhere other than it changed form from liquid water to the gas version of it. Now, we talked a little bit about solubility towards the end there, and it's really the idea of sort of like dissolves like. And that's really the idea that, how one molecule interacts with itself are another molecule. Those are what are referred to as intermolecular forces, which we'll talk about, I think, in a later chapter. Intermolecular forces. And these are really the forces that hold one molecule together with another. And when we talk about like dissolves like, what we're really saying is things are typically soluble in other things that basically behave like they do. So however a particular substance interacts with itself, be that as sometimes what is referred to as hydrogen bonding, dipole-dipole interaction, the way they're able to sort of interact with themselves, if they could find somebody else that basically they could interact the exact same way with, they will be soluble in each other. So what you're really doing is taking, you know, for example, when we have a bunch of waters together, they are held together by what is referred to as hydrogen bonding. And that is a bond between the partially positive side of water, which is hydrogen, and the bond between the oxygen, which is negatively charged. So that is what is referred to as hydrogen bonding. And that is a very strong intermolecular force. So when water goes and interact with other substances, if they can interact in the same sort of way, it makes them very soluble in one another. Thank you. And obviously, if it's something where they don't have that ability to interact like that, they will not be soluble in each other. So I think we also looked at the idea of oil and water. Oil basically is what is referred to as a non-polar molecule. Basically, it's like neutral. It has no charge. So when it gets together with water, they're really trying to interact in two very different ways. And that's why over the long haul, water and oil really doesn't have a way to maintain a relationship together, because all intermolecular forces, as we'll talk about, is a very simple idea of basically positive and negative attraction. That's pretty much how all molecules, intermolecular forces, work to keep together. Positive side of one is attracted to like the negative side of another. So again, when you throw something like oil that's really kind of neutral, has no positive, negative side, and water, which does have sort of a positive, negative side, again, that's really where the trouble sort of comes into play. So what we left on was the idea of solubility, and things are soluble in each other if they are ionic and polar. Again, that is the interaction that occurs with like the salt and water. Things that are polar and polar, they are very soluble in each other, again, because they're either going to be using one of two things, hydrogen bonding or dipole-dipole interaction, which are two very similar intermolecular forces, ways to interact with each other. Also, if you have something that's nonpolar, which is sort of neutral, and something that is nonpolar, they also will be soluble in each other, because again, they basically are interacting with each other the way they interact with themselves, basically through what is referred to as dispersion forces is what they typically use. And those three combinations, if you have those things and you put them together, you would expect them to be soluble, which basically means they should mix together. It should look like a solution. You know, if something's a solid, for example, and it's water, those guys should dissolve in the water and all becomes one solution. If you have two liquids that you mix together and they're soluble, it should all just look like one liquid together. It should be no different layers or anything like that. And obviously the opposite would be if something was insoluble in each other. If you had a solid, it would not dissolve in the liquid. Or if you took two liquids and they mix them together and they're insoluble in each other, you would see layering happen. Sort of different layers occur from the different solutions mixing. So really, as we go to insoluble, it's really only when you sort of cross over from something that is polar and non-polar together, that is definitely when you're going to sort of run into a situation of them really not mixing really well. Questions on the stuff we talked about, I think, last time. Okay, so continuing on with sort of this theme here of solubility, how do we know, for example, in a reaction, if we mix together a couple of things, would we expect like a solid to form? So if you remember, there was a type of double displacement reaction, which basically resulted in a solid being formed, or what is referred to as a precipitate. And those are what are referred to as precipitation reactions. So the way that we could sort of predict whether or not we would get a solid if we sort of mix a couple of things together is we could use what are referred to as solubility rules, like in this table. You have a similar table in your book. But these are solubility rules for really ionic compounds in water. And there are certain things that are soluble. And what that basically means is if you look at this table and determine that something is soluble, it would get the AQ symbol next to it. Basically, it'll be a solution. There would be no solid. It would just be like a regular in the liquid phase, but really a solution. If something is considered based on solubility rules to be insoluble, that means that you would expect a precipitate to form. You would expect a solid to form. And those are typically the guys in sort of equations that get the little S symbol next to it when you do it. So let's take a look at some of these solubility rules. Now, there are certain solubility rules where there's no exceptions. So it's like always that case. There are some where it's mostly soluble or insoluble, but there are some exceptions that would be the opposite. So first off, if you come across any type of compound that contains anybody from group 1 on the periodic table, that's pretty much as far as you need to go. It will be soluble no matter what the situation. There's no exceptions as we see here. So if you come across something like sodium chloride, as soon as you see the sodium in there with the chloride, you will know it's soluble. And this guy would be a solution basically and get the aqueous symbol. Don't have to go any further really than that. Same thing here. If you have something that has ammonium in it, NH4, like ammonium nitrate, NH4NO3, that I think we saw when we were talking about naming. As soon as you see that NH4, it's always going to be soluble, no exceptions. We would expect it to have the aqueous symbol. Anything with nitrates are always going to be soluble as well. And again, there's no exceptions. So if you happen to look at a formula, see something with NO3 in it, you should always expect it to be soluble. Basically, we'll always make a solution in water. Now, when we get to the halogens, our chlorides, our iodides, and our bromides, they are soluble in everything, but there are 3 exceptions. So normally these guys on the left are soluble, but the 3 exceptions would be the opposite of soluble, which means if you have one of these 3 guys with either chloride, bromide, or iodide, it would go from being soluble to being insoluble and would get a solid indication. If it's not one of those 3 guys, then it would be soluble. So for example, up here, our sodium chloride. Chloride is, we want to look at chloride in this case. Soluble in everything except for silver, lead, and mercury. And in this case, that obviously is not silver, lead, or mercury. So it is soluble. Also agrees with the sodium being soluble in this case. So that's why we do have the aqueous there. If we had something like silver chloride, we would look at the chloride, and it is soluble in everything except for silver, lead, or mercury. In this case, it is silver, which means instead of being soluble, it becomes insoluble. And we would actually get a white solid that would form, which would be the silver chloride in this case. Any questions on that so far? Sulfates are soluble in everything except for some group 2 exceptions. So calcium sulfate, barium sulfate. Again, if it is one of these guys in the box, instead of the sulfate being soluble and aqueous, it would also become insoluble in this case and get the solid designation. You would expect some type of solid to form. So these are some things that are typically going to be soluble in solution. Now, there are some things that are typically insoluble. So again, there are these guys at the end here. These guys are normally things that would make a solid. And that is anything that has carbonate in it. So if you find something with carbonate in the formula, you would expect it to be a solid, except for basically the soluble thing that we talked about up front, which means if it has somebody from group 1, it's still going to be soluble. If it has somebody with ammonium, it will also be soluble. So those agree with the top two that we talked about here a second ago. Same thing with phosphate, going to be normally solid with everything, also except for group 1 and ammonium. And lastly, hydroxide typically will be insoluble in everything except for group 1 and some calcium, strontium, and barium are some exceptions to it. So on these guys, if you end up with one of these guys that are normally insoluble, these guys then would become soluble at that point. So these are what are referred to as solubility rules. These are, what we could use to sort of determine an equation. For example, if we basically took two liquids together, would we make a solid? Any questions on that there? So let's see how this sort of works. So we take something like sodium bromide plus lead to chloride. This will be a double displacement reaction where we get some sodium chloride and we get a little PbBr2 in this case, maybe a 2 right there as well. All right, so if we were going to go through our solubility rules here, take a second, use the solubility rules and determine, are each of these soluble aqueous? Are they insoluble and a solid? Let's see what you come up with. You may not be able to find maybe both things on a table like this. Sometimes you will. So looking at the first one, I see sodium, which again, if I come up here, I see that sodium is right there. It is soluble and there's no exceptions. And really at that point, you don't need to go any further because there's no exceptions. We know that this should be soluble and this should get that aqueous symbol next to it. If you wanted to, in this case, you could look at the bromide as well. And if we look at the table, we see bromide is soluble in everything except for silver, lead, and mercury 1. In this case, that's not silver, lead, or mercury 1. So again, they both agree with each other that it should be soluble. Any questions on that there? Looking at the next one here, again, you may not see lead on the left-hand side, but we will see Cl on the left-hand side. And I picked a really bad example, but we'll go with it anyway. So that, we see Cl here is soluble in everything except for silver, lead, and mercury, which in this case, it is lead. And that would make this actually a solid, which makes it a really bad example, but that happens, I suppose. I was gonna go with nitrate, but I chose the wrong thing. So that guy actually would be solid in this case. Our sodium chloride, again, looking at sodium, which again has no exceptions, always gonna be soluble, would be aqueous. And here lead, not gonna be found on the table, but Br will. And again, Br is in the same spot here, and it is soluble in everything except for silver, lead, and mercury. And this guy would be a solid. So pretty bad example there. That should have probably been nitrate, but oh well, I suppose. Any questions on how to use that there? Let's take a look at the bottom, which hopefully I did better. This is barium, which we might not be able to see, but we do see NO3, which is nitrate. And we go to the table and we look at nitrate and we see it's soluble in everything. There's no exception. So that's all we need for that. That guy should get the aqueous symbol. Here, look at the next one. That is potassium, which again is up here on top. That also is soluble in everything. There's no exceptions, which means that really is as far as we need to go on that one. We could also look at the sulfate. Sulfate is soluble in everything except for calcium, strontium, barium, and lead, which is none of the cases here. So again, they both agree with each other. This is again sulfate, which we were just looking at, but in this case, it actually is hooked up with barium, which is one of the exceptions. So sulfate is normally soluble. Because this is an exception, it becomes the opposite and becomes insoluble. And this barium sulfate here would make a solid in this particular case. Yes. Yeah. Would which one be a solid? over here? It would not, because in this case, the barium's actually hooked up with the nitrate. And when we look at the nitrate, which is right here, it is soluble in everything and there's no exceptions. So because it's actually hooked up with nitrate, it would not be solid in that case. It actually only becomes solid because in this second case, it's hooked up with the sulfate, and the sulfate is soluble in everything except calcium, strontium, and barium. So it becomes the opposite. So a lot of times it really is sort of what the thing is sort of hooked up with and determining sort of if you will see a solid or not. Other questions? And lastly here, looking at potassium, which there are no exceptions, and also the second guy there as well, nitrate, there are no exceptions. So both tell us that this guy would be aqueous. So I did much better on that second equation there. Question on how to use solubility rules to figure out what would be the solid. You should be familiar with the solubility rules. They probably will be provided for you. But, you know, common ones like group 1 and nitrates, you know, those are things, you know, you should have some familiar with that. They're typically soluble in everything, you know, they do pop up a lot. Any questions on that? So let's talk a little bit about solutions and solubility. As we talked about previously, molecules, again, that have similar structure tend to form solutions. And again, that idea of like dissolves like, as we talked about last time at the beginning here today. The solubility of a solute in a solvent does depend on temperature. So typically, the higher the temperature, you will gain a larger solubility of a solid in a liquid. Again, by raising the temperature, you're raising the amount of energy that's there, and that's just going to help everybody sort of break apart from each other and sort of start the dissolving process. At a lower temperature, you have a larger solubility of a gas in a liquid. So if we think about gases and a liquid, gas molecules are basically flying around, right? And at lower temperatures, the gas molecule should be moving faster or slower. They should be moving slower at a lower temperature, right? Which means if they're in the liquid part, they are going to stay in that liquid part a lot longer, right? If they were moving a lot faster until they sort of exit out of the liquid part. Pressure also plays a role in the solubility of a gas. At higher pressure, you have a larger solubility of a gas in a liquid, kind of like a soda can, right? Before you pop the soda can, it's under a lot of pressure, and the CO2 that's in there is dissolved in the liquid part of your drink. When you pop the pressure, you do two things. You lower the pressure, allows the gas molecules to get out of solution, and you also provide an escape route for your gas molecules, right? The fizzing you see sometimes when you open a soda can and stuff like that out the top, it's the CO2 coming out of the top of it because it's now less soluble in the liquid part. Also, why your soda goes flat if you leave it out long enough, right? All this CO2 flies out the hole and you go drink it and go, oh, that did not taste so well. Tasted much better when I popped it open the first time. There is, again, a limit to how much solute you can get to dissolve in a solvent, and it is temperature dependent. So at a particular temperature, you know, there is really a limit to how much of that solid you could get completely to dissolve. Again, I think we might have mentioned this last time, you know, if you just take a bunch of sugar packets and just keep dumping them into some water, at some point, you know, even if you mix it in, they're not going to all dissolve. It'll just sort of pile up on the bottom if you really dump a lot of sugar or something, you know, into it. So what happens when we add too much solute to a solvent, we get what is referred to as a saturated solution. And what a saturated solution is a solution that basically has hit the maximum amount of solute that will dissolve at a given temperature. So pretty much you just hit the point, which is sometimes referred to as the saturation point, which basically means we'll call that my saturation point. I'm dissolving, everything's going to dissolve, and boom, I'm going to hit that point where I've hit the maximum amount that I could get to dissolve in that solvent like water. And that means that if you hit a saturated solution and you continue to take more solid and want to dissolve it, it will no longer dissolve. So you'll get that sort of piling up of the solid at that point. Before that situation occurs, we have what is referred to as an unsaturated solution. So an unsaturated solution is one where we have not hit that point of maximum amount I could get to dissolve. So in an unsaturated solution, you're like back here, it will continue to dissolve. It will continue to dissolve until you hit a saturated solution. So an unsaturated solution, you can continue to take solid. It will dissolve in something like water and continue to dissolve until you hit basically that saturation point. And at that point, you have a saturated solution that no more solute will dissolve in it. Any questions on that there? Also, sometimes you could have what is referred to as a supersaturated solution. And a supersaturated solution is kind of what the name implies. It's a super solution now. It is basically a saturated solution. So typically how you make a supersaturated solution is you make a saturated solution. And a lot of times you heat it up. So we just talked about, you know, when you increase the temperature, you get a lot more stuff to dissolve in it. So by heating it up, you could get a lot of solid to dissolve in it. But two things happen as well as you start to heat up a solution. You start to evaporate off some of the water, which is a solvent. So typically to make a supersaturated solution, you start with a saturated solution, kind of heat it up, get a lot of solid dissolved in there. And then basically what you do is you just leave it alone and you let it cool back down. So what happens in this case, at the higher temperature, we could get all this stuff to dissolve in it. And then as it starts to cool back down, what's going to happen is it's going to go, wow, I got like way too much dissolved in me now at this point. It's actually still going to be a solution at this point, but it's going to be a very unstable solution at this point. So unstable that if you just like knock it, or you just take one small crystal, whatever you dissolved in there, super small, you can barely see it, and you drop it in there, it's going to decide, I got too much dissolved at that point. And because it's relatively unstable, what will happen is all the solid will actually just come right out of the solution at that point. So you would have this solution, because it cooled back down, you have way too much dissolved in it. And that's basically the supersaturated solution part of it. And basically it's a very unstable sort of thing. I did a demonstration of it not too long ago, and it was so unstable, I just accidentally tapped it on the desk, and out came all the solid from solution. You basically will go from a solution to like rock hard. You'll be in there, you don't get anything out of it. So that's basically what a supersaturated solution is. Basically a solution that you have way too much solute dissolved in it for that given temperature. And again, they're usually quite unstable type solutions. Any questions on that? Yeah. Yeah.
And lower temp from larger solubility of gas into liquid. What about what makes it small solubility? What is there like a strategy or a name that the lower temp creates low solubility?
No, so it just has to do with the idea of the temperature. If you're talking about sort of the gas and the liquid part, again, the lower temperature part of it, what makes it more soluble at that point is because at a lower temperature, our gas molecules are going to be moving a lot slower, which means as they're in the liquid part, they're going to stay in that liquid part for a lot longer period of time. And that means they're going to be really mixed for a lot longer period of time. And that basically means that their solubility increased because of that. If you increase the temperature, with a gas and a liquid, you're going to get the opposite effect. It's going to have a lot more energy, and it's just going to kind of sail through the liquid part a lot faster. And that means it's not going to stay mixed as fast, as long, and it would be a lot less soluble at a higher temperature than a lower temperature. So that's what that sort of refers to. In the case of a solid in a liquid, the higher temperature really adds a lot more energy, and energy is very useful for getting everybody starting to move and stuff like that. And that's why when you increase the temperature, it also allows for a lot more solid to be dissolved in a liquid portion because of a lot more energy. You know, otherwise at a very low temperatures, things are, you know, together in a solid phase. They're really not moving all that much. So as you increase the temperature, that helps the solid part of it sort of move a little bit more, and that allows it to sort of dissolve a lot better at a higher temperature sometimes. Yep. Other questions? Okay, so there are some other ways we could describe solutions. A concentrated solution is a solution that contains a relatively large amount of solute, and a dilute solution is one that contains a relatively small amount of solute. We're going to talk about molarity here in a bit, but molarity, you might have seen it on some of the bottles that you use in the lab. It has a big M, usually has a number next to it, like, I don't think you see 18M, but it has 18 molar is the concentration versus maybe like 0.1 M or something like that. And the bigger the number, the more concentrated it is. It means it has a lot more moles, if you will, of the solute in the solution than something that's a lot smaller of a number. It's more concentrated at the higher number. And that's typically how solutions come. By the time you get it in a lab, they do dilutions of it, and you have a much lower concentration of most of the things that you use in lab as a more dilute. It's kind of like, you know, you buy the big gulp before class, right, with all the ice, and it tastes really good. It tastes like soda, right? You come to class, a few hours later, you get back to your car, all the ice is melted, and it's hot in your car. You're thirsty, you take a drink, right? Maybe you regret it at that point. And it doesn't taste as, you know, kind of fresh, if you will, right? It tastes a lot more diluted, right? And that's basically how a dilution sort of works. When that ice melts, you just added a lot more water to the mix, right? And it really outweighed like the syrup and all the other stuff that's in the soda. And it obviously tastes a lot weaker, if you will, because it's diluted. And that's sort of what happens with solutions, as we'll talk about with dilutions as well. You know, you add more water or something like that, it brings down the concentration and is not as strong of a solution. Any questions on that there? Okay, so the next thing we want to talk about are what are referred to as electrolytes. Electrolytes are substances that, when they're dissolved in water, will create ions. And these ions, these positive guys, negative guys, really help sort of complete the electrical circuit, if you will. And they typically can conduct electricity. Now, there's some different types of electrolytes. There are ones that are strong electrolytes. So strong electrolytes, when they go for a swim, will 100% break apart into ions. You have absolutely none of the whole unit still together. So if we took something like sodium chloride solution, really when we look at a sodium chloride solution, it is a strong electrolyte. It is 100% going to break apart into sodium ions and chloride ions. So in a solution of sodium chloride, 100% of what you have in that solution are the ions. You have absolutely zero of these guys still together. There's no sodium chloride units still together in solution. They're 100% broken apart. They're surrounded by water, like we talked about earlier. The ions are not together. They're floating around in the solution. You basically just created a lot of ions in that solution, which means this thing is going to conduct electricity very well. Very common experiment, perhaps this week in lab, they hook a light bulb up. I'm gonna make my light bulb square so I don't borrow a bad one. Light bulb has some electrodes on it, and they stick these electrodes with the light bulb into a solution of sodium chloride. It would go off super brightly. Yes, it would be very, very bright. It would conduct electricity really, really well. The light bulb will come on. It will be very bright, and that means it's a strong electrolyte. Acids, some strong acids, ionic compounds. These guys are typically strong electrolytes. That is hydrochloric acid, which is a strong acid. It will 100% break apart into H plus and Cl minus. Again, 100% of what you got going on are the ions that are in solution. thus it would conduct electricity very, very well as well. So a strong electrolyte is typically anything that is ionic, anything that is a strong acid or base. So for example, some strong acids, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid. These are some examples of strong acids. They 100% break apart into ions in solution. They do not stay together. They conduct electricity very, very well. Some strong bases are typically guys that have hydroxide in it, like sodium hydroxide, potassium hydroxide, calcium hydroxide. These guys 100% break apart in solution. They produce 100% ions. They will conduct electricity very, very well. Any question on strong electrolytes here? And again, anything that's typically an ionic compound, usually a strong electrolyte as well. How do you recognize a strong electrolyte? Well, one way is you've got something together on the left-hand side of the arrow. You have a one-way arrow heading towards the product side, and you got ions on this side. So that's a good way to recognize if you're given the equation, is this thing a strong electrolyte or not? That is sort of what you're looking for. Something together on the left, ions on the right, one-way arrow. And if you have an observation like the light bulb went off very, very brightly, then that would be a very good indication that it is a strong electrolyte. Now, there's another type of electrolyte, which is a weak electrolyte. Now, a weak electrolyte, unlike a strong electrolyte, will mainly stay together. But will produce a few ions in solution. So because it's able to produce a few ions in solution, not as much as a strong electrolyte, which 100% breaks apart into ions, is still able to conduct electricity. Using our example here of our light bulb with our electrodes, if we put it into a weak electrolyte, the light bulb would go on, but it would be dim. So it wouldn't be as bright as what you would see with a strong electrolyte, but it would still turn on. Almost look like the light bulb's probably dying. It doesn't turn on very brightly, but it still is able to power up and stuff like that. A lot of weak acids and weak bases are weak electrolytes. So for example, HF, which is hydrofluoric acid, is a weak electrolyte. When it breaks apart in solution, it will break apart into H plus and F minus. Unlike our strong electrolyte, over here on the left-hand side is actually mainly what you have in solution. You have a few of these guys that have been formed. Because it's still able to produce a few of those ions, it'll be able to conduct electricity, but again, nowhere near what a strong electrolyte would be able to do, which is why the light bulb comes off dim looking. If you had something like acetic acid, which is CH3COOH, or sometimes written C2H4O2, same thing. This will break apart into acetate and H plus. Again, in solution, you mainly have this guy still together, but we do produce a little of these guys on this side. So how do you tell the difference if you're given an equation, for example, and it's a weak electrolyte versus a strong electrolyte? Well, if it's ionic, it's probably strong. But if you see one of these guys, here's a couple of things that will definitely point it out to you if you are not looking at an observation. You got one thing on the left, you got ions on the right, and you may be saying that sounds very much like what we just talked about there with the strong electrolyte. But the difference is actually in the arrows. And with a weak electrolyte, you can see that these arrows are heading in both directions. This implies that this reaction is what is referred to as a reversible reaction. So whenever you see two arrows heading in opposite directions, it means a reversible reaction. That means that there is actually what is referred to as a forward direction. And the forward direction is going from reactants to products. In a reversible reaction, what will happen is at some point, the products will build up enough that they will decide we would like to come together with ourselves and go back the other way. And at some point, once you build up enough of the products, you will get the reaction actually heading in the opposite direction, which is what is referred to as the reverse direction. And this will reach what is sometimes referred to as chemical equilibrium, which means as fast as it goes one way, it's going to go back the other way just as fast. So how you recognize sort of a weak electrolyte is if you're doing an observation with the light bulb, it is dim, it is a weak electrolyte. If you're looking at the equation, you will see something on the left, you will see some ions on the right, but you will see these double arrows, one heading in both directions, and that's a really good way to recognize it as a weak electrolyte. So things like hydrofluoric acid, acetic acid are weak acids, some other ones, some nitrous acid is also a weak acid, some carbonic acid, also weak acids. Ammonia as well is NH3. That's a weak base, actually. And that's some of those weak electrolytes. So weak electrolytes will still break apart, but they really do stay together as a whole unit. But because they're able to produce a little bit of ions, still able to conduct electricity, still considered an electrolyte, and will still conduct electricity, but again, very much weaker and dimmer than what you would see with a strong electrolyte. Any questions on that there? One last one is what is referred to as a non-electrolyte. A non-electrolyte basically will dissolve, but will not produce any ions. Because it doesn't produce any ions, there are no ions floating around in that solution, it is unable to really conduct electricity. So it will not conduct electricity. Hence, the light bulb does not go off. So how do you recognize in an equation a non-electrolyte? Well, if you look at something like sugar, which is a non-electrolyte, because it's covalent, it's carbon, hydrogen, oxygen sharing electrons, you could dissolve it in water and you will get sugar that will become a solution, but there's no ions. So typically in the equation, if you look on the left, you look on the right, and it's like the same thing, no ions. Non-electrolyte is pretty much what you're going to see in that case. And here's a better picture of what I drew. So here's our sodium chloride. Again, 100% breaking apart here. Strong electrolyte, light bulb, very, very brightly goes off. Here's our HF, mainly stays together. A few of those ions form. You can see the light bulb still turns on, but looking like it's dying, not a lot of electricity being conducted. And then obviously down here is our non-electrolyte, which is sugar. Light bulb does not turn on in that case. Any question on the different electrolytes? Okay, the next thing we're going to talk about are equivalents. So equivalents, body fluids typically are containing a mixture of several electrolytes. An equivalent is the amount of ion that's equal to 1 mole of the positive or negative charge. So a lot of solutions sometimes are given in what are referred to as 2 common units, equivalents per liter. are what is referred to as milli equivalents per liter. These are sometimes how a solution of electrolytes are given in terms of their concentration. And the way that we typically use equivalents is sort of as a conversion factor to get us into these units. By the way, milli is the same milli conversion that we do like milliliters to liters and things like that. So there should be 1,000 milli equivalents in one equivalent, right? So how do we come up with these actual sort of conversion factors to use? They're really just based off the charge. So if we had something that had a calcium ion in the solution, calcium has a +2 charge, and really the plus doesn't matter here. It's actually just a number, and the number here is 2. And we could come up with a conversion factor that says for 1 mole of calcium ions, there are 2 equivalents. And again, the 2 comes from the actual number on the charge. It doesn't, again, like I said, matter if it is positive or negative. If we had nitrogen there with a -3 charge, we could say 1 mole of nitrogen, or nitride, has 3 equivalents. Again, we could look at sodium, which is +1. 1 mole of sodium ions has 1 equivalent. Also, doesn't matter if it's a polyatomic ion. You know, you could have a polyatomic ion like sulfate. 1 mole of sulfate would give us 2 equivalents. So again, we'll really use this as sort of a conversion factor. It comes just from the actual number on the charge. Doesn't matter if it's positive or negative. And again, 2 very common units are these 2 here, equivalents per liter and milli equivalents per liter. So let's take a look at one just to kind of see, you know, how we would get there. Let's say we had, go back this way, I think. Let's first say we had 0.025 moles per liter of, let's do sodium sulfate solution. And let's say that we wanted to figure out the equivalents per liter and the milli equivalents per liter for both of the ions that are present here. That would be the sodium ion, bless you, and the sulfate ion here. So the first thing that we really want to figure out is, you know, what does this guy sort of break apart into? So this guy here would break apart into a couple of sodium ions, right? That's what the little 2 means. There's 2 sodium ions. And it would also break apart into a sulfate ion. Yeah. So now that we see sort of the ions that it breaks apart into, we could actually come up with our equivalents and mole sort of conversion for each of these. We could see that from our sodium, 1 mole of sodium ions gives me 1 equivalent, right? And again, that comes from the +1 charge or the 1 charge that's there. For our sulfate, like we saw on the previous page, for 1 mole of sulfate, we get 2 equivalents. And again, it is from the 2 that is there on the charge. So that's exactly where it comes from. No real math. So let's start with the sodium ion, right? So in this case, we are given actually the concentration of the whole thing here, but we're actually interested in just the sodium part, right? So we could use a little bit of like stoichiometry to help us get there. And for every 1 mole of the whole thing, right, there would be how many moles of just the sodium ion? There would be 2, right? That's in front there. That would give us 2 moles of the sodium ion. So we could actually use that to convert our concentration of the whole thing to just the sodium. So let's just do that part. So 0.0250 moles per liter of the entire thing. For every 1 mole of the entire thing here, we get 2 moles of just the sodium ion. And that means for just the sodium ions that are floating around in that solution, it would be 0.025 times 2. We would have something like 0.05 moles of just the sodium ions per liter. Any question on that there? Yeah. 2 moles, yeah? Sorry, equals 2 moles of sodium, yeah. Other questions? All right, so what that gave us, and really why we did this, is so we could just really get the concentrations. Really what we're looking at, by the way, what we're looking at is actually what's known as the molarity of the sodium, moles per liter. Just the sodium ion. We could actually do the same thing for sulfate. If we do the whole thing here, 0.025 moles per liter of the entire thing. Bless you. The mole to mole relationship between the whole thing and sulfate is a 1-to-1 relationship, right? For every 1 mole of the whole thing, there is 1 mole of sulfate, right? And if we use that as our conversion, we got 1 mole of the entire thing. Gives me 1 mole of sulfate. That means really my number didn't change. 0.25 moles of sulfate per liter. And again, by the way, that is the molarity of it. So what we have here now is our kind of concentration of each of these ions that are floating around in our solution, but we have it in sort of the wrong units for what we're looking for. We have it in really what is moles per liter, which is molarity. In our case here, we actually want to turn it into how many equivalents per liter that would be, and really how many equivalents per liter it would be for each of them, and how many milli equivalents would it be per liter. So to do that, we're going to use the actual equivalence conversion next to do that part of it. So again, what we saw earlier was in terms of equivalence, we had these 2 relationships. And since I'm out of room, I'm just going to flip the page and continue on here. So what we had was 0.05 moles per liter of sodium ions. And we also had 0.025 moles per liter of sulfate. All right. Using our equivalence relationship for sodium, we saw that for 1 mole, so that the moles cancel of sodium, opposite location of the moles here, we get 1 equivalent, which means the moles would cancel and we would be left with equivalents on top and liters on the bottom. That would be 0.05 equivalents per liter for sodium. Question on that there? Other questions? So again, using that equivalence relationship that we got for the charge, it will allow us really just to change it to a different concentration unit of equivalents per liter versus moles per liter. And we also could convert this into milli equivalents per liter by using the conversion factor we talked about earlier. In 1 equivalent, there would be 1,000 milli equivalents. And if we do that, we will end up with 0.05 times 1,000. Looks like 50 milli equivalents per liter of sodium. So the concentration of the sodium ions that are floating around in this solution is 0.05 equivalents per liter. are 50 milli equivalents per liter. Again, it's just a different sort of concentration unit to represent the sodium ions that are floating around. Any questions on that calculation there? Now, we could do the same thing for sulfate using the relationship that we saw on the previous page to convert our moles per liter into equivalents per liter. And for 1 mole of sulfate, there are 2 equivalents. Again, the 2 comes from the charge. The moles will cancel, and this will give me 0.5. No, I lost the 0 there. 0.50 equivalents per liter of sulfate, which we can also convert into milli equivalents by using the same conversion as above. That 1,000 milli equivalents is 1 equivalent, and that would give us 50 milli equivalents per liter of sulfate. So the concentration of the sulfate that is flying around in that solution is 0.05 equivalents per liter and 50 milli equivalents per liter. What do you notice about the concentration of the positive guy and the negative guy? Are they different or the same? They are the same, and they are the same because when we put together an ionic compound, the overall goal is to make sure that the positive guy and the negative guy's charge equals 0 so that they balance each other. And when you do the concentration of a solution that contains ions like this, and it is a solution that contains positive ions and negative ions, they always should end up with the same concentration in terms of equivalents per liter and milli equivalents per liter, because in a proper ionic compound, all the positive charges and all the negative charges that are floating around that solution to basically cancel out to 0. And that's basically what it does here. All the negative charge in that solution comes to about 0.05 equivalents per liter, which nicely balances out the 0.05 equivalents per liter that's coming from the positive charge. So the overall charges balance each other out. Any questions on that there? Yeah. It comes from the actual charge on the ion. So that is sulfate. And the charge on sulfate is actually -2. And the minus is not important. It's actually the number. So because the number is 2, you could straight up come with a conversion that 1 mole of sulfate will give you 2 equivalents. And that's also where we got the 1 equivalent per liter, 1 equivalent per mole for the sodium, because the sodium has, again, the plus really doesn't matter, but the charge is 1. And 1 mole of sodium ions would basically give you 1 equivalent of charge basically coming into that solution. So that's really, you know, how you get your kind of conversion factor from the actual formula of the ion, the actual charge on the ion. And again, it doesn't matter if it's positive or negative. In this case, it's actually just the number that's the important part. Whatever the number will be the equivalents there are per mole, sort of the relationship there. Other questions on that there? So let's say we had, so let's say we had 0.125 moles per liter of phosphate. What would be the equivalents per liter and the milli equivalents per liter of phosphate? So take a few minutes and see what you come up with. Let's take a look at it. So really you could think of this as sort of a conversion. We need to change the units. The good news is the bottom unit all the way across on everything we were looking for is liters. So we really don't have to touch anything on the bottom. It's just really converting the top to equivalents, and then really from equivalents to milli equivalents. As I mentioned before, moles per liter is a unit known as molarity, which is capital M. And that is probably the most common unit of concentration, which we'll talk about a little bit later on in this chapter. But we're basically starting with the molarity. So to get us to equivalents, we do need to get our kind of equivalence from the charge, and we see that the charge here is 3, and that means that in 1 mole of phosphate, we would have 3 equivalents. So that's really our conversion factor that we're going to use. Again, doesn't matter if it's positive or negative, it's just the number in this case that's important. So we just use sort of a dimensional analysis approach here, starting with what was given to us. We want to go opposites to get rid of what we don't want, which is moles. So on the bottom does need to go moles so that they cancel. Up on top would go our 3 equivalents. At this point, the moles on top and the moles on the bottom would cancel. We basically would be taking 0.125 times it by 3, and that is going to get us 0.375 equivalents per liter of phosphate. So really at this point, that is one of the answers that we were looking for, where we're just, again, using the charge as a conversion factor. Any questions on that there? At this point, we're really just converting prefix units here. We're going from kind of the base unit to milli, which again is our 1,000 milli equivalents is 1 equivalent. So we'll pick up with that number there of 0.375 equivalents per liter. And in this case, again, we'll do opposites. So we want to get rid of equivalents. So 1 equivalent on the bottom, 1,000 milli equivalents up on top. Equivalents on the top and bottom will cancel. And that will leave us times 1,000, looks like 375 milli equivalents per liter of phosphate. Any questions on any of that steps there? So really you can think of equivalents per liter, milli equivalents per liter as a, I'll say, rarely used concentration unit for solutions. They do use it sometimes on IV bags and stuff like that. But it really is just a concentration of the ions that are floating around. And if you do have, like I said before, a solution that's ionic, all your positive guys and all your negative guys should always end up with the same concentration in terms of equivalents per liter. That way everything's balanced. That's a good way to check yourself. If you do a positive guy and a negative guy in the same solution, you get 2 different numbers. Definitely wrong. They should always end up being the same when you're doing these type of units for everything to balance. Any questions on that? Yeah. There. Yeah, so it's a very common one. I think in your lab, they like to do that one, milli equivalents per liter and equivalents per liter. So those 2 are very common ones. A lot of times they'll do that because they'll give a lot of people kind of a nicer whole number than a point number. You know, it's like the last one I think was 50 and this one's 375. So it is a common sort of unit when you're using equivalents to convert it to milli equivalents. Again, just to make it sort of the number a little bit bigger and manageable for people sometimes use. But also this will relate to yeah, so since we're covering it here in class, obviously, so it's fair game for the exam, if that's your question. Yeah. Same question or? Yeah. Say again? The right here? That is not molarity. This is actually a unit of what's referred to as equivalents per liter. What we actually started with over here, that is actually molarity. Moles per liter is a unit of molarity. You could have wrote that number like 0.125 big M phosphate, for example. And basically what the big M means, molarity is moles per liter, is basically how you calculate molarity. And you can convert that big M into a usable number by the number stays with the moles, and it's always per 1 liter on the bottom. So that is how it kind of converts into a usable sort of number. And it's a really good idea, as we'll talk about when we officially talk about molarity. But when you do that, it's a really good idea to get rid of the big M. And a lot of times people don't get rid of the big M when they're doing calculations, when they're using molarity. And they have absolutely no idea where like the liters part of it is, or they forget about the liters part. So as we'll talk about, it's a really good practice to kind of convert it into both units so we could kind of clearly see it. But what we actually started with was actually molarity. and we converted it from molarity, which is the most common unit of concentration, into this, which is, I would say, not so common unit of concentration, but I think covered in your lab and stuff for that. They talk about it. Other questions on that? Yeah. It would depend what the question would be asked. So, I mean, it may ask you for both. So you might need to give both answers, or it may just ask you for one or the other. So in the question, it would ask you to convert it to, you know, what is this in either equivalents per liter or milli equivalents per liter, or both, you know, could be an option. Yeah, it should be. I just kind of boxed it before I wrote the other one, but that should actually be in there with it, because you do want to put what that concentration goes for. So when somebody sees it, they know that goes for the phosphate ions that are floating around the solution. Other questions? So here's just a table from your book that, again, kind of goes over the idea of how we get the sort of relationship. And again, as we talked about, it really is just the charges, the number. And again, that is basically how many equivalents you would have per mole. And really our application of it is using it really as a conversion factor to kind of go to these units and stuff like that. Any questions on equivalence? Okay, so let's talk a little bit about another type of concentration unit. And this is what is known as mass percent, or mass percent. And it's sometimes abbreviated like we see there, percent m/m. And that again means mass to mass percent. To calculate the mass to mass percent of a solution, you take the mass of the solute, and that's the smaller part of the solution, the stuff that's dissolved in there, and you divide it by the mass of the solution and you times it by 100. It's really important in these problems, the bottom part, which is the mass of the solution. If you remember earlier, we talked about the idea that a solution is basically made up of a solute and a solvent. And you do want to make sure that you actually get the mass of both of those guys on the bottom. The reason that is really problematic for a lot of people is in these type of problems, it is very, very common that they will give you the mass of the solute and the mass of the solvent separate from one another. So they'll actually give you those values independent of each other in the problem. And what happens a lot of times is people will end up dividing by just the solvent on the bottom. So you want to make sure that when you divide on the bottom here, that it actually is both of those things together. And again, in a lot of mass to mass percent problems, you actually do need to kind of add those two numbers together to get the guy on the bottom. So that's, again, a very common mistake. People will just look and go, oh, that looks like a big number, I'll just use it, thinking it's the solution, but it really is just the solvent. So you want to make sure you get both of those guys there on the bottom. It's really important. Now, if you had, for example, a 4.5% by mass sodium chloride solution, we can sometimes turn a percentage into a usable unit by assuming 100, right? So if you assume 100 of something, it keeps the number the same. So if you ever needed to, say, turn a percentage concentration into like a conversion factor, if you said you had 4.5% by mass sodium chloride, what that would mean is technically you would have 4.5 grams of sodium chloride in 100 grams of solution. So you could take that percentage and really turn it into a usable type conversion factor, or you can flip it around. You could say in 100 grams of solution, you would have 4.5 grams of sodium chloride. So sometimes in a problem, you may actually be given the mass percent. You could plug and chug into the equation on the bottom there if you want, or you could kind of do a more dimensional analysis and unit sort of way, and you could kind of use the percentage as a conversion factor. Again, the grams go with the number basically, and it's always 100 grams of the solution. Any questions on that there? Why don't we try one here to finish up on? A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. calculate the mass percent of the calcium chloride solution. Take a minute or two, see what you come up with. Okay, so since we're getting to the end, let's take a look. We're looking for the mass percent. So our mass percent is the mass of the solute divided by the mass of the solution times 100%. So when we look at this, we made a solution by taking 2.5 grams of calcium chloride and 50 grams of water. So the solute in this case is, which one? It's the calcium chloride. It is the smaller part, right? So this would be our solute. 50 grams is the larger part, which means our water here would be our solvent in this case. That means obviously we have the mass of the solute given to us, but as we were talking about earlier, we want to add both of those together. So the mass of the solution would be the mass of the solute plus the mass of the solvent, which in this case is 2.5 grams plus 50 grams, giving us 52.5 grams of solution. At this point, we would then have everything we need. So our percent mass to mass would be our 2.5 grams of solute on top. We want to make sure we got our entire mass there of our solution times 100%, going to give us a 4.76 as our answer. Typically, people will leave it as percent m/m, which means percent mass to mass. And we would also maybe put calcium chloride there so we know what we are talking about. Again, very, very common mistake is the bottom number here. People would divide by 50, for example, which is just a solvent. Again, you want to make sure that you really do get the mass of the entire solution. Any questions on any of that there? Okay, we will lay it up there for today.